Hello, my name is Dr. Allison Justice, and I'm with the Cannabis Research Center and Coalition. Today, we're going to talk about and start to unravel the complexities of cannabis drying and curing. So, when I say complex, it is complex. Though we've been growing and drying and curing for many years now and producing very good quality product, the problem is we do not have the science behind what we're actually doing. Until we understand what we're doing, have the tools, and understand the right buttons and knobs to push and change in order to maximize quality, we're just guessing. Now, we're doing pretty good guessing, but when we have the power to understand what those knobs and buttons change and how it improves, that's really when we have power. Now, the problem is, for me, for the industry, is there's no past literature we can look at and lean on to start to understand this process, because there's very little, handful of journals, academic journals out there about drying and curing. And the other problem is, well, we can't really go and look at other crops because nothing is like cannabis. Think about cut flowers. Well, it's not the same thing, because cut flowers, this is a plant organ that we're trying to keep alive for as long as possible, trying to keep the water in it. Tobacco's not exactly the same, because we don't really care about the trichomes. We're not trying to preserve terpenes, so we dry it hot, and that does a lot of interesting things to the plant. So though we can grab from different pieces and different journals and different crops to start to understand what even to test in cannabis, it's very limited. And then it's a wide range of things to test and to be able to narrow down. Now, the bud, the flower of the cannabis plant, it's really broke up into two parts. So you have that leafy, the greenness, the cells with chlorophyll, that have fiber and sugars and all sorts of different compounds that are completing these biochemical changes over time and reduce over time as we dry it and as water becomes less moisture content in the plant. But then we also have these glandular structures, these lipid covered membranes that are so fragile and that are holding this extremely volatile substance that we want to keep. So really, it's a beautiful dance that we have to understand and do just right. And really, it's a shame that more focus hasn't been put to this in terms of scientific understanding, but also in terms of being a commercial producer. You know, a lot of times the dry room is the last thing to be thought about. It's just the extra space in the corner. But really, we need to grasp this, we need to understand this, and we need to do it with skill, because if not, all of that time that's put into growing could certainly become null and void if they're full of microbials, or if they're so dry they're crumbling. So it's something we need to understand, and we really need to perfect for this industry. Now, like any other crop, nothing's one size fits all, just like in growing. It's cultivar dependent. You have colors, you have different trichome densities, you have different densities of plant material. And though we can have trends that are similar, it's not going to be exactly the same. So it's a process that's ever changing, and we're ever learning. And as we learn, applying that to the commercial space is another jump. Is another thing to understand and get just right. Now, I really like to call it post-harvest. Until we understand the definition of the word curing, it's hard to place it. And so hopefully this talk will give you a little bit of insight of the work we've been doing, where we've really been trying to understand what that word means, curing. Because ultimately, what we know is that we dry the plant and then we put it in storage. And in my research and what my theory has brought to my work so far is that curing is really something that stretches throughout. It happens in drying, and you'll see in slides further that a lot of that biochemistry happens early on. But then there are changes that happen slowly, very slowly, once water activity gets down, once the plant's dry. Changes happen, but much slower. So if curing just means change, change is happening throughout, and actually most rapidly at the beginning. So let's talk about drying. What is it? It's water removal. But think about it this way. You've spent 13 weeks growing, nourishing this plant, filling its cells with water. You have a plant, you harvest it, and it loses 80% of its weight by water removal. So you, as a cultivator, as a operator, understanding you have to remove that water, but when you are at that key point, you've got to stop removing that water. Now, it's not just about grams of water equals money, it's also about safety. And so making sure we're removing enough water to where microbials don't continue to grow is very important. It makes for a sellable or non-sellable product. Now, how do we measure water? There's two different ways. There's a water activity meter, which you see there on the right, and a moisture content meter, which you see on the left. Now, there is a huge difference between the cost of these items. But if you're a commercial cultivator, you've got to have a water activity meter, and you've got to understand how to use it and how to harvest at the right time based on water activity. Now we'll go into why that's important. If you're a smaller cultivator, home grower, you can get away with using a moisture content meter. But if this is a professional business, we've got to understand the ins and outs and the science behind why we need to do this, how to do this, and how to make a safe and enjoyable product by understanding all of this. So let's talk about water activity versus moisture content. Now, water activity might not be something you've heard of before, but in the food industry, this is something that is commonly used. It's how they understand when you have a raisin that is dried enough to be safe and not to be sent to someone and it just completely be covered in mold. So water activity is the measure of how much water is available for biological and chemical reactions. So on a scale from 0 to 1. This is really your metric for mold growth, bacteria, your microbials. It's your microbial indicator. But it's also what is looked at when we're understanding enzymatic activities and how some of these processes can keep going, is by that unbound water. It also equates to shelf stability. If you have really, really wet cannabis and you put it in a bag, it's going to mold. And that's because that water is there and available for it to mold, because the spores were already there. So it's about the freedom of water molecules, not how much water is present in total. So let's move on to moisture content. Measured in a percentage, it's the total amount of water in the material. And it's used really for your weights and your yield calculations. The reason I say that is because just because you have two samples with the same moisture content, they could have very different spoilage risks. Same moisture content, one might have a water activity that's higher, one may have a water activity that's lower. So it's very important to understand and keep the two in your mind, separate but understood. Now, a good example of this is a grape, right? You have a grape, it has a limited shelf life. You put it in the refrigerator, it lasts a little longer without molding, but eventually it's going to senesce and die. But if we go through post-harvest steps where we're bringing that water out, now you've all had raisins, you know they're not bone dry. There is some water in there, but that water is tied up it's bound to sugars. So even though that water's there, it's hogging all the water, right? So the microbes can't take that water to grow and to ultimately spoil the raisins. So, very important concept used in food science, and of course, it's a very safe and smart reasoning to use this in cannabis. Now, this is something I show every time I talk about post harvest. This is a stability diagram where we're looking at, on the bottom, you'll see water activity. On the right, you've got the 1, and all the way on the left, you've got 0. 1 would be fresh, completely wet, whereas 0 is bone dry. Now, as you go up on the left and right of the chart, you'll see the relative reaction rate and the moisture content. Then we start to see curves and trend lines in this. And so this just really gives a nice visual of when the plant is really wet, high water activity, the chances, the probability of bacteria, yeast, mold growth is really high. And so keeping that in your mind as you're drying your plant and you're thinking about how fast do I dry it? How slow do I dry it? You're trying to avoid this microbial growth in those first few days. And I'll show you in a few slides of how we do that with the metrics we currently use. But it's important also to keep in mind as water activity goes down, a lot of these enzymatic and non-enzymatic activities start to slow down. Some drop very fast at the higher water activities, where some still remain but very slow down towards the lower water activities. So this is a non-cannabis specific graph, but it's very insightful when we're trying to understand what's going on with cannabis drying. So let's not forget the other important factors at play here besides moisture. So we've got temperature, oxygen, time are the enzymes present. UV exposure, which I've got marked out because we dry and cure in the dark, but UV can be very changing to certain chemicals. But also CO2 and O2 balance. Now, I'm sure you've heard of nitrogen flushing in certain foods, but also I've seen it in cannabis. And there's a reason for that. It reduces the presence of oxygen, which reduces oxidation. So all of these are important, and all we have to keep in mind when growing this plant, drying this plant, and beginning to research this plant. For ages, we've used the metric 60-60. Now that's 60% relative humidity at 60 degrees Fahrenheit. But the problem is that relative humidity is relative, as is in its name, to temperature. So air at 80 degrees can hold way more water than air at 60 degrees, even if it's at the same relative humidity. So that means the drying force is very different, even if the relative humidity is the same, which kind of hides that importance. So look at the table below. You'll see two different temperatures, 60 and 80, and you'll see relative humidity being the same, 60%. But when you look at the vapor pressure deficit, the difference between the amount of vapor that can be held in the air at a certain temperature and the amount that still can be added to that air, that difference there is your true drying force. So vapor pressure deficit is one number, it's a mathematical equation that fuses relative humidity and temperature into a single number. And so that is your driving force. That is the gas, how fast or how slow the air is, the vapor is coming off of that plant material. So that is very important. And so you're able to manipulate RH and temperature, but still achieve your drying force. You shoot for VPD, you manipulate your temperature and your relative humidity based off that. So let's look at this graph put together by Dr. Jim Faust at Clemson. So here he was looking at moisture content over time. I think that goes up to 20 days. And he looked at loads of samples drying at different temperatures and different relative humidities, equating different vapor pressure deficits, and looked at how moisture content changes over days with those different VPDs. And so here you can see really the closest to being 60-60 is right here at 59 degrees Fahrenheit and 55% relative humidity, about a VPD of 0.8. Follow that yellow line here, and we're drying right under 10% moisture content within 10 days. Now keep in mind this was done with a certain number of varieties, and so understanding how your environment does this with your varieties, different amounts of flower, there can be variance, but this is a really good guide to help you understand how long it takes to dry under different VPDs. Now, it's important to know that all drying systems are not the same. There's different square footage, different volume, and different capacities for each unit. Some will add moisture back, some will not. And knowing that and understanding your own system really gives you power. But let's look at some real world data. Now, these are actually from my room, and these are the rooms that were used for the data I'll show moving on. So keep in mind the VPD and temperatures that were used. But even though set points are 60-60, the room doesn't necessarily follow that trend, especially exactly at the plant level. So these are readings from right at stem level, and you can very easily see how temperatures swing, how when dehus are really blasting, temperatures are warmer. It's important to look at VPD here and see how far the swings are going multiple times a day. Now, if you've ever looked at a trichome under the microscope while drying, it's the stalk that dries first. The stalk does not have the oils which the glandular head have. So as the plant's drying, these stalks actually desiccate and twist, and those heads are left to move and pull off each other and cause rupture. So when you have a room that isn't quite controlled as you might want, you certainly will be getting more rupturing and disruption of the trichome heads. The other important thing to look at here is, we're staying at 60% all the way through, but once we get to about day 7, the flower material has lost the greatest amount of water it's wanting to lose, and now it's slowly losing water. And that's how plant material works. It's that bound water is much harder to pull out than the unbound water. But what I want you to really focus on is here, we in this room, there's only dehumidification. So if outside of my room it's 40% humidity, the humidity is only going to continue to go down because the plant is not putting out moisture to keep the moisture in the room up. So if I were to not buck the flower at this point and put it into containers where it doesn't lose any more water, you're going to lose a lot of unexpected water. So watching water activity throughout this time period and catching the stop before it goes way down, if your room is not where it can rehydrate, then that could be a problem. And this is where storage materials and containers come in very handy. Do you know how much CO2 is being accumulated in your rooms during drying. This is something that I found not a lot of people explore, and I understand why. We have CO2 monitors in our grow rooms, but why would you have it in your drying room? The thing is, the levels get really high. Question for you. Do you know how much CO2 is produced in your rooms? What's the concentration held? It's understandable if you don't. Not a lot of people do. We have CO2 monitors in our grow rooms, but why would we have them in our drying rooms? Well, it's important that we do understand, and that's because depending on the type of room you have, it may get to very, very elevated concentrations of CO2. And you might ask, why is that even happening? And it's happening because the plants have been chopped. They know this, and they know they are dying. So they are beginning to feed on themselves, use up their resources, complete a process called respiration, which in turn produces CO2. Now, the CO2 levels, again, in some rooms, depending on leakage, can get really high, the levels that you would apply in a grow room. But what's important to know and understand here is that when CO2 is in concentrations really high, that's also displacing oxygen. And so when oxygen is displaced, like flushing with nitrogen to displace oxygen, you are limiting oxidation and potentially limiting, in a good or bad way, we're not actually sure yet, you're limiting these enzymatic activities. So as we try to understand if having these high concentrations are a good or a bad thing, it's important for you to understand what your rooms do. I've seen some that are extremely sealed, high concentrations get extremely high. I've seen it up to 5,000 parts per million, which could actually be dangerous and is something you should monitor for your personnel. But I've also seen rooms that recycle or that flush the air, fresh air, and the concentrations do not get that high. So again, as we learn this plant, as we understand what some of these metrics do, then we have power to change for good. But the first thing you can do is understand what your room does, because knowledge is power. So next I'm going to go into some experiments we did using a spectrophotometer. Now, spectrophotometer is a device that shines a certain wavelength through a cuvette, which is that there shown in my hand. It's an extraction process to pull out certain compounds, in our case carotenoids, chlorophylls A and B. And when I look at what happens over time in drying, I'm able to see what the absorbance differences is for these pigments. So ultimately I'm saying how green is green, how is chlorophyll changing over time, different types of chlorophyll, and of course carotenoids. This right here is pretty exciting data. Now, when we hear about curing and what it does, you'll hear a lot of people say it's chlorophyll degradation. Well, if you're considering curing the stage after bucking, which is after you've reached the water activity, moisture content you're wanting to achieve, what we're seeing here is not a lot of chlorophyll degradation happens at that point. So looking at this graph, we've got days after harvest going all the way up to, I believe, 35. And then we've got absorbance. Now, this isn't exact concentrations of these pigments, but we can interpolate the amount of absorbance and the differences to represent that pigment. So, for example, we've got chlorophylls A and B here, we've got carotenoids, and we've got, most importantly here, this drastic drop really stopping at about day 10 when we shuck, when we are at a 0.6 or below water activity, enzymatic activity stops. So here we can show, we can prove chlorophyll degradation, of course, unless it was put in light or really high temperatures, it's not going to continue, at least at any reasonable rate, after we have got to the water activity level we're wanting to keep and hold it at. The other thing is really important to note is that these pigments are degrading at almost 80%. So when someone asks and says, chlorophyll's degrading, well, how much? About 75% of the chlorophyll, A and B, as well as carotenoids, are degrading 75%. So this picture actually correlates with the graph here. And you can see here at day 1 where you're very, very green, almost can't see through the liquid. And then here I think this last one here is day 56. And that's a lot of change. So yes, we do degrade chlorophyll, but 90% plus of that degradation happens before the moment when ultimately it's time to pull and go into bucking. So that safe phase, about 0.65, chlorophyll degradation pretty much stops. I wanted to bring these environmental graphs back one more time as we close, just to reiterate the importance of when your job is done. Now, if you consider your job done here once the plant is finished drying, as you see it indicated by the star, then if you stop control when you shuck, you're going to continue to dry that flower out. You're going to lose water, you're going to lose money. So your job's not finished then. Your job's not finished when it goes into the curing bags. You've got to make sure you have control all the way throughout. If you're bringing out pounds at a time for trimmers to trim, if your room that they are sitting in is not controlled to the perfect VPD that this flower needs to stay at its current moisture level, then you're losing money. You're losing quality. Rehydration is not the answer. Just as rehydrating something that's freeze-dried becomes mush, the cells start to become a lot more fragile. Rupturing happens. So the goal is not to dry quick and rehydrate. The goal is to dry, to keep it at that moisture content that you're shooting for. And not forget that that doesn't just mean drying and curing. That means all the way until you're in that finished 8th jar, your finished product where you know that water activity is not going to change. So monitor everything. Monitor your rooms that your trim teams are in. Monitor your rooms that your plants are in, and you will be very successful. So please follow along. There's going to be a big journey to really understand what's happening with drying and curing post-harvest of cannabis. So follow along, many years to come of this work. Please join us for free. We're open source, cannabisrc.org. And of course, follow us on Instagram. We try to post as much as we can, time permitting. Thank you for your time, and keep growing.